When developing a deep learning model, people typically struggle to optimize hyperparameters that affecting the model output in training phase. If the performance is not satisfactory in validation phase, practitioners should go back to the training phase again and again. To address the non-trivial process, AutoML is proposed as a solution. The solution provides various search algorithms to efficiently explore user-defined search spaces. However, people still suffer from the process, since they should configure various settings to maximize the potentials. To support the essential tasks for the process, we propose HyperTendril. The control panel allows users to stop and run the AutoML process quickly. The overview panel shows high-level statistics of the AutoML process, such as performance distribution, optional metric distribution, and trade-off between them. Using this view, users can quickly recognize the general performance of the configured search results, and they can select interesting models to analyze the details of them. The 3 levels of AutoML analytics helps users analyze an AutoML process at different granularities. The search method view is composed of monitoring view of performance improvement and exploration history view of each hyperparameter search space. The monitoring view presents the model performance history as the AutoML process progresses. Using this, users quickly check whether the process is attaining a more optimized model over time. The exploration history view is composed of multiple plots. Each plot for a search space visualizes models as circles with their hyperparameters, and the x-axis presents the iteration index of the AutoML algorithm. To help users understand the behavior of the search algorithm, each model presents its performance history and creation process. In this case, we can see the hyperband method discarded the poor models progressively. The color scale of model performance can be adjusted by the user interactions. In the hyperparameter level, HyperTendril utilizes a parallel coordinates for an overview of the search results and variable analysis for the hyperparameter's importance on the model performance. Here, each axis of hyperparameter is ordered by its importance, and users can activate each of them to see the effective regions. The brush interaction allows users to filter the models and refine the search space. Using this, users can easily learn the effective hyperparameter and its promising region to refine the search spaces for a next optimization process. In addition, HyperTendril provides an interface for the details of the variable analysis through a matrix-based visualization. Each column represents each hyperparameter, and each row represents the effect of the hyperparameter and those interaction effects. When users interact with each row, the details of analysis results are shown, and the parallel coordinates is updated accordingly so that the users can see both views simultaneously. In the model-level analysis, users can validate the training status of individual models with user-defined metrics, where each line represents a model with different colors. The x-axis represents the training step of the model, and the y-axis represents the metric value. Now, we demonstrate how the HyperTendril helps users analyze their hyperparameter optimization processes with 2 case studies. In the first case, the expert optimized RayNet model with 3 hyperparameters and analyzed the results through HyperTendril. He noticed that the best performance scored much lower than its known performance. To check the AutoML method worked properly, he explored method-level analysis view. First, he checked that the model performance continually improved throughout the process. However, he could not resolve why the performances were generally low, so he analyzed detailed behavior of the search algorithm. Through the exploration history view, he observed that the method only focused on training networks with 20 layers and discarded the rest, which have deeper layers. Following the observation, he analyzed the training status of networks, which were randomly sampled at the initial stage of the search algorithm. Through the model analysis view, he noticed that the models were too early compared and terminated by the search algorithm, although the loss function values were not saturated enough. He could learn that the evaluation time should be carefully configured to prevent the AutoML from discarding models at too early stage of training phase. Utilizing the insight, he refined the search algorithm configuration by delaying the evaluation timing and created a new process. After the second process was completed, he could obtain a much more accurate model about 23% higher than the initial process. He also checked that the performance were compared properly. Next, the expert optimized 6 hyperparameters and run an initial AutoML process with Bayesian optimization method. She first checked the results on overview panel for the high-level statistics, and then she tried to identify the effective hyperparameters on the validation accuracy. She first explored the effective hyperparameters by brushing the performance axis in search space view, and she noticed that the lower value of weight decay hyperparameter is related to the higher performance. To analyze in details, she interacted with the hyperparameter box on the top of the search space view. Through the importance and effective region on the parallel coordinates and hyperparameter importance view, she could confirm the lower value region is effective on the performance. To investigate interaction effects with other hyperparameters, she interacted with learning rate, which is highly correlated parameter, with weight decay hyperparameter. She first checked the overall dependency between the 2 parameters through a heat map visualization at the hyperparameter importance view. Next, interacting with the different areas of the weight decay axis on parallel coordinates, she could carefully refine the search space, considering the effect of learning rate hyperparameter together. After that, she could finalize revising the search space of weight decay hyperparameter. Through a similar process, she analyzed the effective areas of other parameters. After the analysis and refinement of all search spaces, she interacted with the control panel to carry out another AutoML process with the modified search spaces. After the second process was completed, she noticed that the best performance is improved. In addition, she also observed that the performance distribution is more stable than before, implying that the refined search spaces yield generally good performance on her task. Satisfied with the results, she decided to finish the optimization process.